So, dear students, let us start the next chapter, that is called the semiconductor theory. Here, first we will discuss about the conductor, insulator, and semiconductor. Let us first discuss about the conductor. A conductor is a matter which has a huge number of free electrons. When a small external energy is applied across a conductor, the free electron move freely through the conductor, starts flowing current. As we know that in case of metallic conductor, they are highly conductive because there exists a large number of electrons, huge number of free electrons. So as soon as they get the thermal energy or heat energy, they starts moving here and there. That's why they are highly conductive. So what are the properties of high conductivity material? If conductor is highly conductive, then what should be the properties of these materials? It should have less resistivity, first. Second, less temperature coefficient. Third, good mechanical strength and high withstand tensile force elongation, and absence of brittleness with good flexibility with tolerable mechanical as well electrical load. Fourth is the rollability and dryability. Fifth is the easy to weld and solder with the low melting point, even it should withstand high current density. And last one is the it does not affect by resistance. So these are the important properties of a conductor. Let us now discuss about the semiconductor. So as you can see in the word itself, that semiconductor is a matter that has a very few electrons at room temperature. Hence, they are neither a good conductor nor the good insulator. Silicon and germanium have mostly used the materials in semiconductor technology. It is easily and cheaply available material in the earth, and that's why all electronics materials cost is very less. Silicon and germanium are the principal semiconductor material widely used in the manufacturing of devices such as transistors and integrated circuits. So as we know that importance of the semiconductor, today's power electronics is dependent upon the semiconductor theory. All the fast switching devices which we are using nowadays, they are based on the semiconductor devices. For example, such as a transistor, MOSFET, GFET, IGBT, they all are semiconductor devices, and they are very fast switching devices. These are the modern devices which are available, and because of that we have gained a most efficient technology in the power electronics design. So semiconductor property is that semiconductor conductivity lies between the insulator and conductor. We will discuss so many things about the semiconductor in coming topics. Now let us discuss what is the insulator. Already I have discussed the various properties of insulators in the previous lecture. So here also let us define further what is insulator. Insulators are the poor conductor of the electricity. It does not have free electrons in the valence event at the ambient temperature or room temperature. Due to this, it can't help to flow of current. Examples are glass, plastics, rubber, paper, mica, varnish, etc. And all types of gases. Here mica and varnish is the most used insulation material in motor winding technology. So this was the example of what are the materials comes under the insulator. Now here one thing we can discuss, that a dielectric also possesses the property of insulator and another is an insulator. So what is the difference between both? Because both are the insulator, but what is the difference between both? The difference lies that a dielectric acts as an insulator, but dielectrics also hold the charge. If we talk about the capacitor, so in between the two plates of the capacitor there is a dielectric medium. So if you apply a voltage across the capacitor, then dielectric assists the holding of the charge. However, in case of insulator also doesn't allow the current to flow or pass through insulator, but it does not hold the charge. That is the main difference between the insulator and dielectric. So what are the properties of insulating material? That is, first is it should have a high dielectric strength. Second, high resistivity. Third, low dielectrics. Fourth, high temperature withstand. And fifth is the high thermal conductivity. So these are the various properties of insulators. Now let us discuss the intrinsic semiconductors. As we know that there are two types of semiconductors, intrinsic and extrinsic semiconductors. Extrinsic semiconductors are further classified as a p-type semiconductor or n-type semiconductor. Here we will discuss about the intrinsic semiconductor. They are the pure semiconductor, and normally they don't have free electrons to move here and there. So in normal temperature they doesn't exist any conductivity in the intrinsic semiconductor. So how we can define? An intrinsic semiconductor is a pure semiconductor, that is a sample without any impurity. It does not have any impurity, that's why it is a pure semiconductor. At absolute zero, it is essentially an insulator, though with a much smaller band gap. However, at any finite temperature, there are some charge carriers are thermally excited and contributing to conductivity. What it means that in normal temperature there is no any charge carriers and they have a very small band gap. However, if they get some finite temperature, then what will happen? These charge carriers are thermally excited and they contribute the smaller conductivity. So semiconductors such as silicon and germanium, which belongs to group 4th of the periodic table, are covalently bonded with each atom of silicon or germanium, sharing an electron with 4 neighbors. A bond picture of silicon is shown in figure, where a silicon atom and its neighbor shares a pair of electrons in covalent bonding. That's why there is no free electrons are available in intrinsic semiconductor. A diagram of covalent bonded intrinsic semiconductor with silicon is shown here. This is the picture of intrinsic semiconductor having a silicon atoms. They are bonded from each other. That's why they don't have any free electrons available for conductivity. That's why they are called the intrinsic semiconductors. Now let us define the extrinsic semiconductor. So in case of extrinsic semiconductor, we want to add some impurity, and by adding some impurity means we want to increase its conductivity. That is the main motive to add the impurity in the pure intrinsic semiconductor material. And once we add the impurity to the intrinsic semiconductor material, they become the extrinsic semiconductors. So an extrinsic semiconductor is formed by adding impurities called dopant to an intrinsic semiconductor to modify the former electrical properties. There are two types of such impurities. That is, those which provide electrons as majority carriers are known as n-type semiconductor, and those which provide holes as majority carrier, they are called as p-type semiconductor. So already I have discussed in the previous classes that previous slide, that extrinsic semiconductors are classified two types, that is n-type semiconductor and p-type semiconductor. Now how we will make n-type semiconductor and p-type semiconductor, that we will discuss here. So an n-type semiconductor is created when pure semiconductor like silicon and germanium are doped with pentavalent elements, as can be seen in the image or a figure, that when a pentavalent atom takes the place of silicon atom, 4 of its electrons bond with 4 of neighbors of silicon atom. However, the 5th electron remains loosely bound to the parent atom. Thereby, this electron can move in the lattice even at room temperature also. So what we want to say, that a silicon atom having a 4 atoms in the outer orbit, and the pentavalent atom having a 5th electron in this outer orbit. So 4 of these electrons will try to share the 4 of the silicon atom electrons, but still one electron will remain alone, because there is no any pair going to exist for that electron. So that electrons remain loosely held along with the parent atom, and thereby this electron can move freely in the lattice even though at the room temperature. Normally, if we provide a temperature, then electrons are thermally excited and they jump from one orbit to another orbit, or they take part in the conduction. But in room temperature, nothing happens. So here, this loosely held electron can move in lattice even at room temperature. If we don't increase the temperature, that is at normal room temperature, then also this electron can move freely. That's why in n-type semiconductor, the majority carriers are the electrons and they move freely in n-type semiconductor, and that's why the conductivity increases. This is the structure of n-type semiconductor. So what is shown as, each silicon atom is shown in the structure, and one arsenic atom has been shared in between the 4 silicon atoms, and 1 electron remains free. This electron even at normal temperature can move freely in the lattice structure. That's why this significance is known as n-type semiconductor, where an pentavalent impurity has been added with the silicon to form a n-type semiconductor material. Now we'll talk about the p-type semiconductor material. So in p-type semiconductor material, majority carriers are holes, and the conduction takes part because of the holes in p-type semiconductor. So a p-type semiconductor is created when a trivalent atoms are used to dope pure semiconductor like silicon and germanium. As can be seen in the image or in the figure, that when a trivalent atom takes the place of a silicon atom, three of its electrons bond with three neighbors of Si atoms. However, there is no electron to bond with the fourth silicon atom. It means three of electrons of trivalent body can be shared with silicon of 3 electrons, and fourth electron of silicon remain alone. There is no further electron which can have a sharing with the fourth electron. So what will happen? This leads to a hole. It means there exists a hole or a vacancy between the trivalent and the fourth silicon atom. This hole initiates a jump of electron from outer orbit of the atom in the neighborhood to fill the vacancy. So what happened? These holes, the neighbor atom electrons try to fill the vacancy of this hole. So from the neighbor atom, one electron jumps and fill up these holes or fill up this vacancy. So this creates a hole at the site from where the electron jumps. Now from where the bond is broken and electron jumps to fill this vacancy, so another hole is created from that covalent bond structure. So in simple words, we can say a hole is now available for conduction. So what happened here, that to fill a vacancy, an electron hole pair is broken and electron has jumped to fill up that vacancy, and that has created a hole for conduction. So it is important to remember that the number of holes made available by the dopant atom is independent of the ambient temperature and primarily depends on the doping level. So what it means to say, that number of holes present for conduction in p-type semiconductor material, they are independent of the ambient temperature, but they depends on the doping level. If you increase the doping level, then these hole carriers will increase in the p-type semiconductor. So this is what we have defined the p-type semiconductor, and this is a structure of p-type semiconductor, that once electrons jump from here to fill the vacancy, one hole is created here because of electron jumping. So if we have a further doping impurity, there will be more holes created in this structure, and this way large number of holes will be available in p-type semiconductor. That's why in p-type semiconductor they are called the extrinsic semiconductor, and there are the majority carriers of holes, and in case of n-type semiconductor there are majority carriers of electrons. So they depend on the what type of atom we are giving a doping to the silicon atom. So that is what about this lecture, that we have defined the conductor, insulator and semiconductor and various types of semiconductors, how we can create a n-type and p-type semiconductor. So that's about this lecture.